On this computer. Okay, welcome back. Chemistry 2341. We're talking about getting ready for our first test. So as of today, you have until 6 p.m. to go ahead and log into your mock test. When you go into Top Hat, you should be assigned mock test 1A or mock test 1B. Okay, the key here is to log in, make sure that everything works. It's going to ask you to kind of scan the room, show that there's nobody there, and I will send out an email with, did I send it out with the recommended things that they ask you to do for this? I thought I sent an email that said, you know, shut down your computer ahead of time and start it back up and close all your tabs. Did I send that email out on Friday? Yes. Okay, good. For a minute there, I thought I forgot it. Okay, so it has,
hey, Lonnie.
All right, here you go.
So it has all these recommendations for you.
Have a nice day.
You too.
And I'm gonna mute you there. Okay, so it has all these recommendations that make things run smooth. You know, have a picture ID. It does not have to be your student ID. It can be a driver's license. And again, this is being video recorded and only AI watches this. This is not live. And so only if there's a extreme level of suspicion that you switch out, or you keep looking away, or they hear people talking to you. That's kind of that kind of stuff. So that's what it's looking for in those particular aspects. So those open up today. Actually, they're open up right now, but we want to sit in class first, and then you'll have till 6 p.m. If anything doesn't work, contact Top Hat support, and they will figure out how to make it work. Okay, either you can lower the resolution on your camera, you can find better bandwidth or something like that. I'm going to do it again on Wednesday. We're going to have a mock test on Wednesday. If it didn't work for you today and you had to do something else, we'll do it again. I want to make sure that you are comfortable with the testing platform before the exam on Friday. And yes, our exam is on Friday. Okay. So, and it is, let's see, we'll have the whole hour to take it. We're going to take it during regular class time. And so I'm targeting 25 multiple choice questions over modules 1, 2, 3, and 4. And that includes module 2.2, which is the IR, spectroscopy. There's will be a couple questions on there specifically focused on where do the functional groups show up on that chart. The mock is not for a grade. It's just to make sure all your computer parts are working correctly. Okay, so today we're going to do module 4. On Wednesday, we're going to review over the highlights of the different chapters and things that I think I should draw your attention to. Nick would also like to do a pitch for SI recruiting on Wednesday. And then for that, the homework for module 4 is due on Wednesday night. Now, the reason I wanted to do it Wednesday night is because as soon as you finish it, you have Thursday and Friday to review it. So all of your homework should be available for review, and look at that in the style in which I'm going to be asking these questions, okay? Do we need to download anything before taking the exam like Proctorio? Yes, you must have Proctorio and Google Chrome on your computer. Okay, in the list of instructions I sent out on Friday, it is the Proctorio plugin for Google Chrome. You can only use those two, and they suggest you have all other things closed, and so that makes it easier for it to monitor that. Okay, did that answer your question?
Okay. Do we have to have the Zoom call open? No.
I'm sorry, what?
Do we have to have the Zoom call open, or do we just start the test at 10?
No, that is a different type of testing. This is Proctorio does the whole thing for you, and so it's just you and the computer. Nobody's looking over your shoulder. Nobody's doing anything. It's just you and the computer.
So we don't sign in like Friday. We don't come to class. We just start the Zoom.
Correct. On Friday, you just go to your Top Hat and log into Top Hat, and then log into the exam. And you'll have the full hour to take it. So I would recommend starting it early. I will be live monitoring, so if you have a question, go ahead and email me. I can answer questions by email for the time. And so hopefully there will be no computer glitches. However, if there's a computer glitch, I do have a workaround, but that's what these 2 mock exams are for, to make sure we cover all of that. Okay. So that's right. There is no class, no Zoom class on Friday, only the exam. Okay. And I'll release the second mock exam on Wednesday after this class, so that we can make, and again, you don't have to take the second one, only if you were having difficulties with it before, or you're uncomfortable with it and you wanted to make sure. Okay. So this is a low stress, no points. It's all it is making sure you're comfortable with the format. Okay. So those are what we have this week. Let's see, on Wednesday, I will have what I consider the top topics for each chapter. Like, this is the main topic, and all the auxiliary topics that kind of go underneath it, knowing, how they kind of interrelate. And I'll have a kind of an outline of that, a visual outline of how that all works together. Okay. So if anybody has any more questions, go ahead and put them into the chat here, and I'm going to pull up my Module 4 slides, which should be on Canvas. Let me double check that. I'm almost positive I put them on Canvas, but they are also on these slides are also on Top Hat. So there we go. All right, share screen. All right, trying to share screen here. All right, I've got the gallery view over here on my left, so I can see there. You can raise your hand, of course, in the participant screen, or you can ask questions for that. Are you recording post on YouTube page for Module 4? Yeah, this recording will be uploaded probably within 30 minutes after class, so that we will have that available to us. Okay. So yeah, the recording and the slides are already posted, and the recording will be posted after. Okay, so up to now, we did a lot of work on nomenclature and learning different functional groups. Okay, now the key here is that these are the functional groups we need to know, and as we go forward here, we're going to add chemistry to each of these things, how each of these different functional groups react. Okay, but before we do that, we have another thing we need to talk about, and that is configuration and how these molecules, when we typically draw them, especially in skeletal form or stick form, we do the little zigzag here. Okay, the key here is that that's an idealized formula, and typically it's what we call our lowest energy formula. But I want to show you that they can be written in a number of different ways, and why we typically write it in that formula, and what it means by lowest energy formula. Okay, so now the cool thing about sigma bonds is, because it's only a single bond and you have the pi overlap between an sp3 hybridized orbital and sp3 hybridized orbital in a carbon-carbon bond, that has free rotation. So you can draw that any of these bonds in any order you want to, and because they have that free rotation, all of the conformers that you can draw are true. And not only are all the conformers you draw true, but at some point in time, they actually exist. They hardly ever exist in that fully extended form. They're constantly moving, constantly dynamic, and so that you can draw them in any way you want. And even the most convoluted kind of balled up structure, and I bet it is like that at least some of the time. Okay, now what makes it want to kind of expand? And that has everything to do with what's nearby in space. Okay, and so what we want to look at is which of these are favored and why they're favored. So what we call this is conformational analysis. And in conformational analysis, we actually analyze which position we should rotate this bond to give us our least energy possible, and understand that there's an energy barrier when we do these rotations. So let's talk about that specifically. Okay, so In our sigma bonds, if we look at our simplest alkane here with 2 carbons, we have this ethane. And you have to remember that those hydrogens are going to be in that tetrahedral shape, right? And so they are spread out as far as they can. Now, the other thing to remember is the outsides of each of those hydrogens have an electron shell on them. So those electrons are actually repulsing each other as much as possible. That's why they're in that tetrahedral shape. But that's going to play a role in how they're going to rotate. Is there an induced dipole when the bond spins? No. When the bond spins, you're looking at an energy difference is that the electrons are repulsing each other from the next atoms over, and then they come to a more energy acceptable position. Technically, we're not changing the dipole. If we do, it's very, very tiny, and it's not a driving force. Okay? So in this case here, we want to have the hydrogens, or any group, spread out as much as possible. So if we look at our drawing here of just this ethane right here, if we just drew it out there, again, in skeletal structure, it looked like that. But we need to add those hydrogens there to show us what's going to happen there. And so what we want to do is we want to be able to space these out as far as possible. Now, one way to draw that is this second drawing here, in what we call a sawhorse configuration. And it starts to get the idea that you want these to be out of sync with these over here, okay? And so to really drive that different perspective home, we have what we call the Newman projection, okay? In the Newman projection, which is this last one over here, we take our first carbon, which is facing toward us, and we have the 3 groups that are on it. And then we draw a circle to represent the carbon behind it, okay? And then we have the hydrogens associated with the carbon behind it, just as these little sticks coming off of the sphere. Okay, why do we do this? Okay, when we do a Newman projection like this, it allows us to see the configuration of all the different groups. Okay, doesn't matter what the groups are. Now, in its lowest energy configuration, if all these numbers 1 through 6 are identical in size, they're going to want to be in this particular configuration. And the angle between this right here is 60 degrees. Okay. Now, the reason this is the lowest energy is that this is taking up space. Each of these is taking up space. And now we're staggering those electron clouds as much as we can. So when we stagger those electron clouds as much as we can, there's the least amount of repulsion between those clouds, and that's how we get this staggered configuration. And so if we're looking down the carbon-carbon bond, we're looking down this carbon-carbon bond, and this is a symbol for an I here, you can see that these groups are going to be spread out, and they are going to look like this configuration. Now, what can influence how this works? Well, as we change those hydrogens out to larger groups, we have to take into account that size of that larger group. Okay. So when we take a look at this, we want to look at a thing called the dihedral angle. Okay, a dihedral angle is an angle made up actually out of 4 atoms. Okay. So in the case of the dihedral angle here, we have a total of 4 angles associated with it. We have this hydrogen, the carbon, this other carbon, and this other hydrogen. So the angle difference between those 2 hydrogens, if we look down that bond, that's what we call the dihedral angle, okay? And that has to be related to those 4 atoms in conjunction. So if we look at our Newman projection again, we'll see that that dihedral angle is like what I said before, 60 degrees. Now that's if all the groups are exactly the same size. Okay? Now, when we have that 60 degrees where all of them are spread out like this, we have what we call a staggered configuration, okay, or conformation. Okay, so in a staggered conformation, that is as spread out as you can have, and you have an equal 60 degrees around each. Where would the carbons be in a Newman projection? great question. In a Newman projection, let's see, the other one is, do you use Newman projections if there are more than 2 carbons? Yes, you can, and we will on the next slide. Okay, so in a Newman projection, the carbon is signified as the carbon closest to what we're looking at is signified by this dot here, or that intersection between those 3 hydrogens. And those 3 hydrogens that go all the way to that dot are attached to that first carbon. So imagine we're looking at this carbon in this direction, and this dot is our first one. And so that is there, and these 3 hydrogens are the ones here. Okay. Now, the big circle represents the carbon behind it, okay? And the little sticks coming out of there represent the hydrogens attached to the back carbon, okay? When we do these Newman projections, we typically only go down 2 carbons. If we have other carbons, those are gonna act as substituents on our ring, on our Newman projection. So we'll see like a carbon up here and a carbon over here if we have 2 other carbons attached to this. Newman projection always goes down 2 carbon atoms, and then all the other carbons in the system are somehow on a substituent somewhere. All right, so let's look at that. If that one we saw where they were 60-degree dihedral angles is called the staggered configuration or conformation because they are separated as much as they can. If we rotate those 60 degrees, we now have a new concept where the dihedral angle is now 0 because we've rotated one of those 2 carbons, and we now have what we call the eclipsed formation. It's like the sun crossing in front of the moon, and so you have them overlapping each other. So the groups are overlapping each other, okay? And so that's how we get to the eclipsed formation, okay? Now, that's really easy to see when we draw it as the Newman configuration. Okay, now, if we want to see the eclipsed form in that dashed and solid wedge configuration that we talked about before on drawing 3-dimensional structures, the solid wedge here is a solid wedge indicates it's sticking out of the plane of the paper. A straight line is indicating that it is in the plane of the paper. And a dashed line is indicating it's behind the plane of the paper. So that's how we get that 3-dimensionality with those dashed wedges and those solid wedges. Now, we can tell that we have a staggered configuration in this dashed and wedge if our bonds that are in the plane of the paper make this little kind of Z structure here. That means that that hydrogen is in the plane of the paper up and the other one's in the plane of the paper down, and that is our staggered configuration. Now, if they're both on the same side, then that would be a eclipsed formation using that. And then all we have to do is rotate 60 degrees and we can go from staggered to eclipsed in any part, which means we go eclipsed to staggered, eclipsed to staggered, eclipsed to staggered as we go all the way around the system. Okay? So let's start with the energies associated with having these go from our staggered through our eclipsed state, okay? So the energy that it takes to make it go from our lowest energy state, which is our staggered state, to rotate it 60 degrees. Now, these hydrogens are starting to repulse each other through space. And with all the other hydrogens, okay, so these 2 hydrogens here are starting to repulse each other in space, okay? So they're starting to push out. So they're trying to get out of that 109.5 degrees. And the energy associated with that electron-electron repulsion is 4 kcals per mole, okay? Now, that's just for those 2 hydrogens. That means when you rotate such that all 3 sets of hydrogens are eclipsed, that means it's a total energy difference from the staggered state to this eclipsed state of 12 kcals per mole, because we have 4 kcals per mole for 3 different hydrogen pairs. Okay. Now, because these are being forced out, it's acting like torquing it out. We call this torsional strain. Okay, torsional strain is forcing this out. And so just with hydrogens, it's 12 kcals per mole. But if the group is larger, that strain will be higher. Okay, so let's look at the energy as a function of just ethylene rotating around from the end. Okay, so let's start with configuration number 1 here. And we're only going to mark 2 hydrogens to show where they are as they move all the way around, because we're freely rotating 360 degrees around. And let's look at the energy as it does this. So if we start here, our relative potential energy in our staggered state is 0. Okay, it's a relative, it's not an actual number. So as we start to stagger these, all 3 sets of these are staggered, which means we have a difference in 12 kcals per mole. Sorry, is it joules? Yeah. It's kcals, right? Yeah, kilojoules. No, it's kilojoules per mole, okay? And then as that hydrogen now slips past, as that hydrogen slips past that dihedral and goes into the next staggered position, which is this one right here, we return to that relative low potential energy. And then as this hydrogen starts to impinge upon this one here, we again regain that 12 kcals per mole. And as it continues to rotate down to this, now it's 180 degrees, or that's more than that. It's a whole, almost all the way around now, and it's back to that equal potential energy. And then again, as we rotate around and then get it back to its original position, we ended up with that same relative thing. Notice each of those are the same height because each of the interactions are the same. We have a hydrogen, 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 and hydrogen, hydrogen. Each time we go through that that eclipsed state. And then when it comes back down to that dihedral state, it's the same interactions. Okay. So think in your head that, okay, if that's true for having them all the same size, I think this energy diagram is a little different if we have things that are different sizes. So think about that. Okay, so to help us visualize that, let's go ahead and use something with more than 2 carbons, like was suggested in the Zoom chat here. Okay, what we're going to do is we're going to look at something that is has just 2 extra carbons on here, but we're going to look down a single carbon-carbon bond. Okay, and we're going to choose the 2,3 bond, which is the middle one. And so we're going to have a methyl group on one of the carbons in our Newman projection, and we're going to have a methyl group on the other carbon projection. Okay, so 12 kcals in energy is only expressed during the eclipse conformation. So that is the energy barrier to go from the staggered to eclipsed with hydrogens only. So there's a question in the Zoom chat, so 12 kcals of energy is only expressed during, it takes 12 kcals of energy to get it to go from its staggered to its eclipsed, and then it can go back into either other staggered. So it's you had to add that much more energy to the system to get it to rotate. Okay, does that answer the question? Okay, now let's go ahead and look at 4 carbons in our system. Okay, so in this analysis here, what we've done is we've taken our Newman projection, and again, we're running on the 2 and the 3 carbons. So if let's look at our wedge structure down here. Okay, so this is our 2 carbon and this is our 3 carbon, such that we have 1 methyl group on either end. Okay, so we now have a group bigger than hydrogen that might be impinging on groups that are hydrogen or might be bigger than hydrogen. So let's start looking at those different configurations, and they actually have slightly different names. Okay, so in this first configuration, right here, this is our starting configuration here. And this is what we call anti, okay? So it's in a staggered configuration, but the two largest groups are 180 degrees apart. See how this group here in the front is on top, and this group in the back here is on the bottom. They are as far apart as you can get them, okay? So this is what we call the anti-configuration, or the most stable staggered configuration, because there's the least amount of electron repulsion with those large groups. If we rotate this 60 degrees, what we get now is our methyl group and this hydrogen are starting to butt up against each other. And this methyl group and that hydrogen are starting to butt up against each other. And these two hydrogens are starting to butt up against each other, okay? So to do that, because the methyl groups are larger, it takes more energy. And so we actually have 16 kcal per mole less stable than the original configuration. So the methyl groups are bigger than hydrogen, and therefore they're creating more torsional strain. Okay. Now notice in this case, we only have a hydrogen methyl, and two hydrogens. Okay. So that once we rotate 60 degrees and we get to what we call the gauche state. The gauche state is where your two biggest ones are 60 degrees apart, okay? Now, once we're in our more stable state, if we call this our relative state at 0 kcal, kilojoules relative here, this configuration, because those two big groups are now within, can create that torsion, that torsion angle of 60 degrees, and they're both bigger than hydrogen, there's actually more torsional stress on there. And so that makes this 3.8 kilojoules per mole higher in energy than our system here. So that makes it less stable than the anti. Okay, it's higher in energy, so it's less stable. So we started at anti right here. We went to eclipsed, and then we went to gauche. Okay, now let's go to the extreme where we have the two methyl groups are now eclipsed on each other. Okay. So with these two methyl groups eclipsed on each other, those are forcing it a lot apart. But then we have to add in the two over here that are both 4 kcals each. And so in our eclipsed, with the two methyls impinging upon each other, our highest energy added to the system is now 19 kilojoules per mole, less stable or more energy than the anti. So let's look at what that looks like on the wedges right here. And let's just look specifically at where the groups that are in the plane are, okay? So all we have to do is look, and let me do a different color here, green, okay? So this methyl group is in the plane with these two carbons, which is in the plane here, and that gives us our anti-configuration, okay? So this one, we have our methyl group in the plane of the paper, we have our two carbons in the plane of the paper, and we have a hydrogen in that plane of the paper, meaning that methyl group has come out toward us, and this is our eclipsed configuration. Okay, I got a question here. In each state, is less energy than anti plus the one before it, or is it just the energy from anti? These are relative from the anti state, okay? Okay, so if we want to call anti-0 relative number, that means our eclipsed is plus 16 kilojoules, our gauche is plus 3.8 kilojoules, and our eclipsed with the two methyl groups is plus 19 kilojoules from that anti-state, okay? Why is the rotation of 120 degrees so much less than rotating 60 degrees? I don't understand that. Why is the rotation of 120 degrees much less energy than, okay, I see what you're talking about. So here we have an eclipsed state where we have the groups eclipsing each other. All three different groups are eclipsing each other. By going that 160 degrees, we've obtained another, it's a staggered state, but it has two of the larger groups together. So we went from a staggered state to an eclipsed state to a staggered state with the two largest groups next to each other. And yes, the increase in potential energy is due to electron repulsion by those two groups, the methyl groups themselves. And the smaller amount is from the hydrogens because they're smaller in size, but it's still electron-electron repulsion. Okay. So if we look at this state here, so this is the 60 degrees first, then the 120. If we look at that, we have the three things that are in the plane here are the methyl and a hydrogen again, and this methyl group is sticking out toward us. But see how those two methyl groups are now kind of close together? They're 60 degrees apart, which means these two big groups are impinging upon each other, and that's where we're getting that energy difference from the anti. Those two methyl groups that are that close together are giving that extra 3.8 kilojoules. Okay? And then when we twist it just 60 degrees more, that's our highest energy state. The two largest groups are eclipsed upon each other. Okay. So if we did this on a map and looked at the energy difference, the energy difference would be different because we never go all the way back down to zero, because we always have a larger group than hydrogen in our system, and we have to account for that. And so if we do that analysis and look at where we're starting in our anti-state here, if we go to our first eclipse state, we have methyl group hydrogen, methyl group hydrogen, hydrogen, hydrogen. So each of these methyl groups is 6 kilojoules per mole. This is 4 kilojoules per mole for a total of 16. Now, when we come back down, the angle here, this is 3.8 kilojoules all by itself. And so we never go back down to zero because those methyl groups are too close to each other and are giving us that electron repulsion. Now, when we go back up right here, now we have 4 kilojoules for this one, 4 kilojoules for this one, and this, because the two methyl groups are there, that's 11 kilojoules for a total of 19 kilojoules above the anti. And then when we come to the next one, we still have these two methyl groups near each other, and that's giving us that 3.8 kilojoules. And then going again, staggering again, giving us, this is 4, this is 6, this is 6, giving us our 16, until we finally have rotated 360 degrees to get us back to our anti-configuration at the end, okay? So we're gonna go from anti to staggered to gauche. Let me star these. Anti to staggered to gauche to staggered to gauche to staggered to anti. So you're going to continue going all the way around until you get all the way back to zero. And again, we're only looking at the rotation around the bond between C2 and C3, the two middle carbon bonds. All right. So now that we see that there's an energy configuration, and even though these can freely rotate, there's usually enough heat at room temperature to allow these to rotate all the way through these cycles here, we see that there is an energy barrier to do this. So if you started cooling these down, you're going to see less of these in the conformation of the highest energies, and you're going to see more of these in the lower energy configurations. Okay. So what if we removed that free rotation and restricted it something by having it in a ring? Okay. We're going to see some of the same configurational energy barriers we saw in the free rotation, but now we're restrained by how we can do it in a ring. Okay. So in a cycloalkane, we're trying to keep that 109.5 degrees at sp3. However, if it's forced below that, we have what we call ring strain. If it's forced out of that, so it's bigger, that's what we call ring strain. Any force because of that ring that makes it go bigger or smaller makes it have an extra barrier of energy, or what we call ring strain. And so we can actually measure ring strain by combusting the materials and seeing how much. However, not all cycloalkanes have the same relative stability, because like for a 4-membered ring, you have 90-degree angles. That's out of the 105. For a five-membered ring, you actually have about 109 degrees. Six-membered ring, you can get all of them at 109.5 degrees. So each different cyclohexane actually has a different relative stability. Okay, so how do we know this? And what we know is that if we look at the heat of combustion, basically the amount of heat given off when we burn something, that tells us the total amount of potential energy those chemical bonds had when they were in that compound. Okay, so if we look at this straight chain butane, okay, 4 carbons, we have, the 4n plus 2 hydrogens on it, and we combust it completely to CO2 and water, we end up getting 2,877, I believe those are kilojoules, yeah, kilojoules per mole, okay? So that's how much heat is released in that system. Now, if we take an isomer of this, which is this, all we do is move a methyl group over to the number 2, and so we have this isobutylene right here, we actually get less energy out. Less heat is generated from the system. So what does this mean? What this means is that this gave off more heat, okay? But because this gave off less heat, it means it must have been more stable because it had less internal energy, less potential energy to give off, and therefore it was the more stable version of it. Okay. Or, I'm sorry, isomer of it. Okay. So whenever you're looking at these relative scales, think of that the negative means you're giving out heat, and the higher the number, the more heat it gave off. Okay. And I'm irrelevant, not including this negative charge. So if the more negative it is, the more heat it gave off, and the more potential energy it had stored. Okay. So now, if combustion is all about stability of the material, and we just showed it in a straight chain, when we start looking at rings, we can actually calculate the strain by how much different it would have been compared with the straight chain. So if we look at this right here, so if we had a 3-membered ring, oops, let me change colors here. We had a 3-membered ring here, and we burned it. It has 3 carbons in it, and so we would expect it to have a certain amount of energy based on the carbons. We found that it actually gives off more heat than it should have, and when it gives off more heat than it should have, that means it had more potential energy, and that more potential energy was what we call ring strain, which means that staggered shapes are more stable. No, staggered shapes staggered shapes are less stable. I'm sorry, yeah, staggered shapes are more stable, right? And the most staggered, the anti-configuration, is always the most stable within a set. I was answering a question in the Zoom chat there. Okay, so, and think about it, a 3-membered ring, these are 90-degree angles. It wants to be 109.5. So that deviation from that 109.5 to that is what is called a ring strain, and we can actually measure it in the combustion. If we go to cyclobutane, these are 90-degree angles, and so we can see that change is actually combust at 109 kilojoules per mole, more than it should have, meaning it was less stable, and that instability is what we call ring strain. When we get to 5, it's getting pretty close to 109. It's about 100 they're 120, so it's getting closer right there, but there's still a little bit of ring strain associated with it, about 27 kilojoules per mole. But now when we get to the rings of 6, we have a couple different conformations that allow it to get completely in that 109 configuration. When it gets completely in that 109 configuration, we actually have no ring strain. Now, as we go up, because of the different conformations that are available to it, And because that it can't be evenly, that has to be twisted sort of weirdly to try to get as many of the 109s as possible, we actually see an increase in the ring strain for those larger rings. Okay. When accounting for the number of carbons in each of those chains. So I have a question in the chat. So staggered shapes are more stable? And yes, they are. But remember that that is a free rotation. So that means that when that molecule combusts, it's still butane. And it's going to combust to give us that much energy. Only the different conformational isomer, where we've moved apart, we've changed a bond, does that account for greater or less chemical stability. And ring strain has everything to do with the idea that the potential energy difference between having it being a straight chain and being constrained into a chain, constrained in a way in which it can't get that 109.5. Okay, so in each of these small chains, we're trying to get them smaller than 109.5, and in the bigger ones, they're trying to get find a way to try to have as many at 109.5 as possible, but it's difficult. Okay, I think that answered your question, right? Okay, so, and this all kind of comes down to the idea that we have a forced ring and we actually end up with a forced staggered configuration. Okay, so let's move up from cyclopropane all the way up to cyclohexane. If we look at cyclohexane and accounted for each of the carbons in it, we saw that it had 0 ring strain. It was the most stable of the monocyclic rings, okay? And it has the least amount of torsional strain and angular strain, okay? The reason we have the least amount of torsional strain is because the way we can move the bonds such that the carbon hydrogens are always in the staggered configuration when we get that system. But we can't always do that in the other rings. For example, in the case of cyclopropane, we are in a fixed position where these are as close to as close as possible to each other. So these are fixed in that eclipsed state. Okay, so being fixed in that eclipsed state means it has to have higher energy in the system. It doesn't have free rotation. It can't go to a different possible. So ring strain is a relation to the difference in combustion to the straight chain, the equivalent number. Well, technically it's the equivalent number of CH2s. So if we took what the combustion for a CH2 group would be, and we measure that, and then we account for 6 of them in a ring of 6, it's the difference in what our theoretical number versus our measured number is. So it's not technically the straight chain, because in a straight chain you'd have 2 more hydrogens. Okay? All right, so why is cyclohexane so stable? Okay, in cyclohexane, we can actually configure it such that all of the carbons are going to be pretty much in a gauche or anti-form, and all of the hydrogens are going to be able to get into that staggered configuration. Okay, but there's not only one conformation available to us in cyclohexane. The most stable one is what we call the chair position. And I'm going to use this as a nice example. Chair is usually the most stable system, and so we're looking to draw it in this way such that we can find the most stable area to put all the substituents. Okay. Now, when we convert from one to the next, there's a high energy barrier. So in the case of going from the chair to the half chair, we actually have to pull down these 2 bonds, take them out, and turn 5 of these bonds in a flat plane, and only one of the carbons above that. Okay, you're forcing a whole bunch of those atoms now into that staggered configuration, And we actually see it's a 20, 50, 45 kilojoules per mole to get to that position, okay? Which means in a hot liquid, you're gonna have some of it being in that chair conformation, going from chair to chair and back and forth, okay? Now, if we then take this little point here and push it up a little bit, we get to what we call the twist boat, okay? In this twist boat, there have a lot of them being in staggered configuration, but some of them are kind of gauche, where this carbon here and this carbon here would be gauche. They would be kind of 60 degrees apart. And so this is why it's fairly lower energy than the half chair, where we have a lot of things overlapping. But it's also not the same as chair, okay? Because we do have gauche. In chair, we have them all as staggered. The next configuration is if we flatten this out, we just move this bond down, we get what we call boat. And so you have 2 carbons up and then the 4 carbons down forming the base. And this is higher energy than the chair, but less though than the twist boat, because now we have this carbon and this carbon are now in the eclipsed form. And so you can think that those are going to cause it to be higher in energy. So now if we move one of these up and one of these down, we get back to the twist boat in the other configuration. And then by flipping this down, we'll get to the half chair, which is again a high energy conformation. And then by flipping this all the way down, we'll be getting to our chair configuration. Okay. So just going, we haven't broken any bonds, we haven't rotated any bonds. All we've done is moved our bonds such that they're going through the gauche, the eclipsed, the gauche, the eclipsed, until we're down to the as close to anti as we can get. And technically, the chair can never get into a full anti. It's just what we call the most relaxed gauche configuration. So let's look at that in a little more detail. Okay. So instead of looking at the chair as that thing that looks like this, okay, let's add some hydrogens to it. And so we can see why this is the lowest configuration possible. Okay. So in this configuration, we have 2 different types of hydrogens. Okay. We have these red hydrogens here. And then we have these blue hydrogens here and here, okay? So the red hydrogens are the ones that are basically sticking out around the edge of that thing. And so we call it the equatorial position, okay? So it's the one that is like the equator of the Earth. They're the ones sticking out. So there's 6 of those that are sticking out that way. And then the ones that are pointing up and down, notice they're all parallel to each other, the blue ones here. We call those axial. So imagine you had the axis of the Earth going through here. Anything parallel with the axis of that cyclohexane Earth are going to be axial positions. And anything that sticks out from that is going to be our equatorial positions. Okay. So now we have names for them. Let's use our Newman projection to look down a couple of those bonds to see what kind of interaction we have. Okay. So if we look down our Newman projection, notice how all of the equatorials here they're not straight out, they're just pointing toward the outside. And that all the axials are actually parallel, but not overlapping. Okay. So the next most important thing we need to look at is which positions are gauche. And if we look at it this way, we have this carbon here, it's coming out toward us because it meets in the middle, so it's the one closest to us, is coming out toward us. And this carbon here is going back away from us. But notice that those carbons are in that gauche position, okay? So they are staggered, but they are close together here, okay? This is the minimum energy conformation we can get, is having this 2 carbons gauche to each other. And if we look from the other bond side, we again have those same 2 carbons being gauche to each other. And so this is our most stable state, okay? We have no angle strain because all of our bonds are 109 degrees. We have no torsional strain because all of our CHs are perfectly staggered. Okay. Now, it's gauche, but there's no way we can draw cyclohexane where we don't have at least one gauche configuration. But as we go through the different rotations, we're going to end up going through different overlapping positions where we have the eclipse positions where carbons are eclipsing each other, and those are the higher energy states. Okay, let's see. Let me just show you how it's slightly different in the boat configuration. We have different names for these, and then I'll go ahead and end because we're right at 1050. So in the boat configuration, it is 30 kilojoules less stable than the chair position, okay? And the reason for that is the fact that we now have two of our systems overlapping completely. So we have eclipsed bonds. And so if we look at the Newman projection, we have the carbon in front of us going to this front carbon, the carbon behind it. So these two are eclipsed now. Remember, they were gauche before, and now they're eclipsed. Also, our hydrogens are all eclipsed as well. Okay, so because we have our two carbons eclipsed, the one in front and the one behind, and our four hydrogens eclipsed, that's why it's higher in energy. But the other thing about that is we don't have equatorial and axials only, okay? We have one new position called the flagpole position, okay? And that's those two hydrogens that are basically pointing up like they would be flags at the front and the back of the boat. And the fact that they're hitting each other is that additional energy that we see in that configuration, okay? Now, in theory, there's no ring strain because all of our bonds are at 190 degrees, but we do have eclipsed hydrogens and eclipsed carbons. The eclipse part is what's giving it the higher energy, not ring strain. Okay, I want to stop there and answer questions, and then we'll continue on this on Wednesday, and then we'll have time for the review. All right, so I'm going to stop recording.